Yeah, my name is Greg. I'm here to tell you about work we've been doing at Low Risk to kind of make open silicon kind of like a commercial reality in terms of used in actual shipping products. And we're doing this via a process we have dubbed the Silicon Commons, which we developed through a project called OpenTitan, which is a big open silicon project. So where are we today with open silicon? So first of all, just kind of defining what I'm talking about when I say open silicon. What I mean here is the chip design that we're doing, our system Verilog RTL, for instance, is actually being made available under an open license. We use Apache 2. Obviously, many licenses are available. But unlike open software, you know, as was covered in the intro from Alison, we don't really see much open silicon in the wild. Open software is a very well-established, mature thing that is used everywhere. Open silicon, kind of not so much. You know, most people probably think it barely exists. Talk to most people in the industry, they probably won't even know what you're talking about. However, I think there's actually a lot more in use than you might realize, certainly from conversations I have with people at kind of trade shows, conferences, conversations with low-risk partners, etc. There's actually quite a lot of people who are looking at available open silicon and using it a bit in their designs. But a lot of this stuff just isn't visible. They don't tell everyone about it. The companies don't say anything about it. It's just getting used somewhere. So I think there's more deployed than you might expect, but it's kind of hard to find out about. And open silicon itself has actually also been around for many years. You know, various examples to point to, but it's mostly been part of kind of academic communities and kind of enthusiasts rather than the industry picking it up. So one example would be OpenRISC. This is an open CPU architecture, kind of like RISC-V. It's also got an open implementation of that CPU architecture. I think that was started around about the turn of the millennium, maybe kind of 98, 99, 2000. This resulted in a website called OpenCores, which I guess was kind of aiming to be the GitHub of open silicon of the early 2000s. Didn't quite pan out that way, but you know, it was an early example of work in the open silicon field. And this also spawned off the Free and Open Source Silicon Foundation. I think another key thing to understand about open silicon, again covered in the introduction, is how RISC-V fits into it. There is a common misconception that RISC-V is open silicon. RISC-V isn't open silicon, it is an open architecture, or you know, an open specification. Anyone can go along and implement it without having to pay anyone any license fees. But it doesn't mean the actual silicon implementation is open. You know, most RISC-V companies are producing standard proprietary closed hardware. However, RISC-V really is a big enabler for open silicon because it makes it a lot easier for you to be able to build open CPUs, and it makes it a lot easier for you to be able to build open systems around those CPUs. So a question I'm going to begin to address is, you know, why don't we see open silicon used more? People understand and recognize the benefits of open software, and it is deployed very widely. Why aren't we seeing the same kind of thing in silicon? It kind of comes down to the constraints. There are different constraints in how you build silicon. So a major thing here is DV, design verification. You need to make sure the system you are building is like fully functional and bug-free. And the standards are very, very high here, especially compared to, say, your typical software standards. So for a commercial tape-out, so by a tape-out, I mean the process via which you produce files that you send off to a silicon foundry to actually manufacture the chip. The standards are very, very high for what you need to achieve because a tape-out is an incredibly expensive process and it's got a long lead time. You mess it up, you need to redo it, you know. You could be looking at 3, 6, maybe even 12 months delay because of that needs to get a new design iteration out to your fab and get a new chip. So this means that no one's actually going to commit to using your design unless they've already got very high confidence it's going to work. And you get that high confidence in part from all of this DV work. And the tooling that is required to be able to do this DV work, as well as various other aspects of silicon design, like the silicon implementation flow, it's all very expensive and proprietary, and it can be quite hard to get hold of. It's expensive, and even if you're like, yes, I will pay $10,000, $20,000 for that tool, you can't just hand your credit card over and buy it like you can for other software. You've got to go through sales channels at Cadence and Synopsys. So for someone who isn't already in the industry or doesn't know much about how it works, even getting access to the tools, even if you have a bunch of money, can actually be quite hard. And open tooling exists here, but you know, right now it isn't really up to the required standards or has all the features you might need to do like a proper commercial tape out. I would note I'm not trying to kind of dunk on open EDA tooling here. There's some really fantastic work happening in this space. We do actually use at low risk some of these tools on a daily basis. And it's great to see the development there, and we're big supporters of it. But you know, we do need to acknowledge that there is a big kind of capability and indeed credibility gap between current state of open tooling in this space versus commercial offerings and what, you know, a standard commercial company will consider acceptable for something if they're considering it for a proper tape out. We can also compare silicon versus software. Again, it's a bit of a mistake to just say open software. We know how to do that. Let's just do the same thing and we've got open silicon. Fantastic, right? Well, there's some fundamental differences that you need to kind of get to grips with. So as I was saying on the last slide, our costs here are very high. So to produce a physical chip, it costs a lot of money. It takes a lot of time. And this means that you can't stand off with the kind of maybe standard kind of open software working model where you can get one person or a small group of people who are like, I'm going to build a program to do this. I'm going to make it open source. They can build it. It can be a bit of a mess. It can have some bugs. It isn't documented. It's got rough edges. But that's fine because it can do the thing they want it to do. And they use it. They iterate on it. More people come in. It builds and builds. And that allows you to build, in the end, a very impressive piece of open source software, starting from very humble beginnings. You can't really do that with chip design. I can't make my like slightly dodgy CPU and then use it in my laptop on a daily basis. I need to, you know, it needs to do an awful lot to get to the point where you can even get your kind of bit of working silicon that a few people might be able to use. And the barriers to entry here are also very high because, as I said, getting access to tooling, even if you have the money, can be quite tricky. And also even learning how you do silicon design outside of industry can be hard. Obviously, you know, you can learn some of this stuff at university, but say compared to software, there's a lot fewer kind of open and free resources or even paid for resources out there. Nowadays, if someone's like, I want to learn how to write software, there's a wealth of really high quality material online and they can kind of just get stuck in. With silicon, there's a lot less of that. So it's just a lot harder for anyone to get involved in this. And so our mission at Low Risk is we want to make commercial open silicon a reality. And by a reality, I mean kind of like how open source software is a reality in the commercial world. It is, you know, open source software is very credible and is seen as like a foundational technology for a lot of what the software industry does. It is not the same in the silicon world, and we think it would be a lot better for the industry if it embraced open silicon. And it occupied a similar position as open software does in the software industry. So how are we doing this? Well, the first major thing that we have been working on is OpenTitan. So this is the main project of Low Risk, and this is our main source of funding. I should say Low Risk is a community interest company, so that's somewhere halfway between a charity and a for-profit company. So we're funded by industry partners. We don't sell things as such, and everything we do is made fully open source. And OpenTitan is effectively the big pilot project that we hope will prove the open silicon model. So what it is dubbing it an open silicon secure execution environment. You can think of it kind of like at least the first output of the OpenTitan project, kind of like a secure microcontroller. There's a lot of applications for this, one of which would be a root of trust, also things like kind of TPMs, smart cards, SIM cards, all kinds of places that you could use OpenTitan technology. And as it is called OpenTitan, everything is open. So the RTL, that's the actual chip design, along with the firmware, the tooling, documentation, all of the tests, all of our design verification, all of the collateral to go along with it is available under an Apache 2 license. And it's been built by a partnership of people. And I think this is really crucial. On the right-hand side, you can see the various industry partners that are involved in OpenTitan. And all of these companies have been putting in various resources, both in terms of money and engineering, to help build this. And I think this is critical because it helps build credibility. And it also helps build trust. So when these companies are involved in OpenTitan, they know that our engineers have actually had a hand in building this and kind of know how it all works internally. That helps them build trust that they can actually use it in shipping product. Low risk's part in this is we host the governance model. So we're not in charge, we just host the governance model. So we help things like the steering committee run. I'll talk about that in a minute. And we also provide a bunch of the engineering resource. So we've got about 20-something people, and the vast majority of them are engineers working on OpenTitan and other projects. However, a lot of the engineering has also come in from our partners here. And at its core, OpenTitan is a large collection of different IP blocks. So there's a whole bunch of different things in here. So there's some fairly specialized security things like AES, various crypto accelerators, cryptographically secure random number generators, more general stuff, things like I2C, SPI, USB, and we also have a RISC-V CPU called IBEX. It's been around about 5 years now. Almost 6 years, yes. So it started in 2018, and the repository went public in 2019. The first focus of the OpenTitan project was a discrete product called Earl Grey. So that's going to be a discrete chip, and that is your kind of secure microcontroller with a whole bunch of functionality. However, it isn't all about that discrete chip. That is simply the first output. We've recently announced we're going to have an integrated solution. This is where you take this collection of OpenTitan IP and you integrate it into various systems. So one example is you'd integrate it into a large SoC that might be used to say kind of data center class machines. Another example is you might integrate OpenTitan technology into smaller things. So, you will note G&D Mobile Security is one of our partners, and they do a lot of work in things like smart cards and SIM cards. So that's another potential avenue for OpenTitan technology. Now, this talk isn't actually about OpenTitan, so I'm not really going to dive into any more detail, but look on the website, and indeed look on the repository, and there's lots more information to find, or come chat to me after the talk. And so with OpenTitan, we utilize an open development model. Our repository is hosted in GitHub. And crucially, that is our active development repository. So you'll see all of our daily work from engineers happening in there, chatting away on issues, putting in pull requests, doing code review. This maybe doesn't sound very novel to someone who talks about open software, but certainly this is very novel in the silicon world. And you do see other open silicon projects where they tend to do a bit more of a throw it over the wall style, where they will build something internally. They might put it on GitHub, but it's kind of like using GitHub more as a kind of glorified tarball release. They have their single commit, here is the project. Or, they might update it once every 3 or 6 months as they make some changes. The actual development is somewhere else that isn't public. We don't do that at OpenTitan. Live development, you can go see what we're doing on a daily basis. I believe it's the most active silicon project on GitHub. On the right-hand side there, you can see roughly last month, kind of dashboard of activity. Had over hundreds of interactions across kind of hundreds of issues and PRs, 37 contributors, over 1,000 files changed. Over the project lifetime, got about 1.5 million lines of code in there, 20,000 commits, 165 contributors. So there's a lot of stuff that has gone into this. And OpenTitan is now a very kind of mature project that has a lot of all of our IP has reached a very kind of high quality level of verification, suitable for a production tape out. And we utilize code review to maintain quality standards. So here's what the talk's actually about, is Silicon Commons. So what Silicon Commons is basically taking the model that we have been developing in OpenTitan and producing it as a more general method for how we at Low Risk think you should develop open silicon. And we've kind of demonstrated that it works through the OpenTitan project. So it's all about developing open silicon using collaborative engineering. So that's one of the really key points. It only works if you get multiple partners coming together to build things. And it draws heavily from existing open software working practices. But as I said, you can't just copy paste it over. You have to acknowledge that there are differences between software and silicon. So you have to take these into account to actually get to the point where you're taping out commercial chips. And I think OpenTitan is going to be a really fantastic proof point to gain credibility for open silicon. So the success of OpenTitan will pave the way for the success of future open silicon projects. So some key concepts in Silicon Commons. So right at the top here, I have governance. You've got a whole bunch of partners, various members of industry. Sometimes they're competitors. So you need a governance structure to make this all work well. So at the top, we have a project director who runs a steering committee who ultimately control the project. Below them, you have a technical committee and working groups. Technical committee are kind of ruling on the high-level technical decisions, and the working groups are the ones who are actually kind of getting into the details and ultimately getting all the work done. And your partnership here involves various companies, academics, other groups, and individuals. Licensing, we publish everything under an Apache 2.0 license, and again, I think this is quite crucial that you are actually making everything available under an open license. It's not just, well, here's the RTL, but you have to pay us for the DV, or you can't even see the DV. No, you can't have the firmware, can't have the documentation. That's not so good. You need to make sure everything is being published under an open license. As I said, I think it's very important you have a repository that allows you to develop in the open. We use GitHub, other options are available. We have contributors. Some of these people will come from partner companies, some of these people are low-risk employees, and then there are contributors from other places. So in particular, we've had quite a lot of interest from various academics who have actually been helping us improve the kind of first iteration of the OpenTitan design. And then we have a subset of contributors called the committers. These are the people who are responsible for allowing commits to be merged into the repository. So it is a committer's responsibility to ensure that the code review process has been properly obeyed before they hit that big merge button. Other key concepts, so I've been talking about collateral. So by this, I mean things like documentation, tests, training material, all of this kind of stuff. When you're trying to say that my open silicon design is credible, people are going to be saying, well, you know, going to be looking at a DV. Where's your test plan? Where's your coverage plan? It's very useful to be able to point to those things. In particular, if a company wants to use the technology and they want to extend it, if you've got all that available for them, they can just pick it up and they can add a little bit on the bottom that does the extra bit they need, turn the handle, and they can get a fully verified design without having to start from scratch. So it's really important this stuff is available to actually make this useful. Otherwise, people won't pick it up and want to use it. Verification, as I said, absolutely critical. We have a well-defined set of development stages in OpenTitan that we export into the Silicon Commons model. So this tells you how you kind of various milestones that you need to get to and saying what you need to achieve in terms of kind of test pass rates, coverage rates, how well developed your test plan is, how well developed your coverage plan is, have you got the documentation, the specification, you know, big long checklists of all the things you need to do. And this kind of mirrors how projects tend to be run in industry. And then we have dashboards. You can see one on the right-hand side here. This is the OpenTitan top-level design verification dashboard. We run regular regressions. There's currently a couple of OpenTitan regressions running a week. Runs, I think, over 40,000 tests. And then we publish all the results. And you can go on and have a look. And we've got our test pass rates and our coverage. We also use CI to ensure that everything that gets committed into the repository has met some kind of minimum quality standards. This full regression takes hours and a lot of compute, so you can't run it for every single commit. But we have a CI process that takes about 3 hours at the moment that runs various tests on software, various smoke tests on hardware. We actually have a bunch of FPGA boards in low risk, and it synthesizes the design and runs your change design on the FPGA to check it's all working correctly. So we have a pretty kind of significant amount of CI infrastructure in place. And then finally, you need a whole bunch of processes to tie this all together. So how do you make decisions at a kind of governance level, technical decision making? We've got an RFC process, so you can put a proposal together, which is then agreed by a working group, may then need to be signed off by the technical committee or potentially the steering committee, depending on exactly what parts of the project it touches. We need an on-call triage system. This is people looking at our regression dashboards and realizing that has broken, it needs fixing. If you don't do that, your lovely sea of green slowly starts kind of going orange, yellow, red as tests slowly kind of break apart, which is just kind of naturally what happens as the project evolves. And we also need an approval process for who is actually allowed to commit to this repository, as well as a process for, well, who needs to be taken off the committer list. Because kind of people come and go in the project, and you need to, part of establishing the credibility and allowing people to trust what you've built is ensuring that you've got good processes around who's actually allowed to commit code into the repository. So my colleague Mano will be talking in a second a lot more about this, but this is another project low-risk are doing called the Sunburst project. And I think it's a really great example of open silicon in action. So last year, Microsoft published a thing called Chariot Ibex. It's a derivative of the RISC-V CPU used in OpenTitan called IBEX, which itself actually came to the OpenTitan project from ETH Zurich and the Pulp project, where it was named Zero Risky. So it's got kind of a long pedigree, kind of, again, generated from an open silicon background. And what Microsoft did is they added these things called capabilities, which greatly improve your memory safety. So they're very good for avoiding many security bugs that you might find in common hardware. And this is based on work that has been done at Cambridge University, known as Cherry. And Microsoft have done a derivative of Cherry and implemented it on IBEX. And there's been a lot of interest in Cherry, in particular in the IoT and operational technology spaces. So operational technology is kind of industrial IoT, IoT running your power plants and your power grid. You need good security there, and there's a lot of worries that the security is not good enough. Hence the interest in Cherry and capabilities. So the UK government have funded us to do some pilot projects that aim to push Cherry IBEX to a point where it can get picked up and we can see commercial adoption of the design. And the first output of that is the Sonata board, which I have one here, flashing away. So this is all open hardware, so the PCB and layout of this is all fully available. The RTL for the system that runs on the FPGA is currently being developed. It's going to be built around Cherry IBEX, and ultimately what it's going to give you is a microcontroller-like system using this Cherry architecture. And I think it's a really great proof point of the Silicon Commons model, because we've started off with this CPU being built by some academics, picked up by us and the OpenTitan project, and kind of quality level elevated to the point it's usable for commercial tape-outs. Attracts the attention of Microsoft, obviously very kind of notable company, and they have enough confidence to build their own stuff on top of it. And then they've kind of come back to us to say, hey, look, we've built this, and then we're getting more funding from the UK government to develop it further, and it kind of comes back to the Silicon Commons. So we've already got this kind of nice cycle of research and development and industry producing better technology. So what does the future hold for open silicon? Well, I think it's very interesting that you're actually seeing a significant and growing interest in custom silicon across the industry. Notice the likes of kind of Google, Microsoft, Amazon, Meta, as well as other large companies. They're all building custom silicon. They're all building their own AI accelerators and GPUs and CPUs and video encoders and decoders. And I think, 10, 15 years ago, people would have thought it'd be madness to build your own chips, but now everyone wants to do it. And I think this is a really great time for open silicon to shine, because what it can do is it can help provide the foundational technology that allows companies to then get on and kind of innovate in the little niche that they actually want to do something in. Going back to OpenTitan, a lot of people need a root of trust for whatever it is they're building. Most companies don't want to build a root of trust, but they do need one that they can rely on. Through open silicon, they can get one that they can rely on, and then get on and build the thing they actually want to build. Exactly in the same way that, very few companies build their own operating systems. Everyone just uses the Linux kernel because, well, why wouldn't you? But in order to get this kind of glorious open silicon future, it's very important that we get contributions in from industry. Low risk has only got to where it's got because of the generous funding that has been provided by industry. A bunch of that has come from Google, but a bunch of that has also come from, well, other OpenTitan partners, also people like the UK government. And I think it can give you a really faster pace of innovation. We've already seen in OpenTitan, before we've really got the first proper design out the door, shipping in products, we've already had collaborations of academics who have been pointing out potential issues and flaws and ways we could do things better. And we've already improved the design. That's before we've got, production version 1 out the door. And we're also seeing it in the Sunburst project. So I think that, OpenTitan it's been going on for quite a while now, and it's really poised to start to become a major kind of disruptive force in secure silicon. And in turn, that will provide a major proof point for open silicon that will hopefully launch a bunch more open silicon projects. So yes, watch this space. Great, and yeah, that's everything. Thank you.